Hey there, and welcome. Today we're going to talk about a really special number. I mean, it's woven into the very fabric of, well, pretty much everything that grows, from the spirals in a seashell to the interest in your bank account. It's so fundamental it gets its own name, E. So let's start with a little thought experiment. What if you had something that was growing all the time? Not in little jumps, but just smoothly, continuously. Is there a single number out there that could perfectly describe that kind of growth? You bet there is, and that's what we're here to unpack today. All right, let's get into it. You know how some numbers are basically math celebrities? I'm talking about pi, right? Everyone knows pi. Well, think of E as being on that same A list. It's a universal constant, and it shows up everywhere, from finance to physics. So where does this number even come from? It's actually a pretty cool idea. Imagine you have $1, and it earns 100% interest over a year. Simple, right? You'd have $2. But what if you got that interest paid out twice a year? Or 1,000 times? A million? This formula right here shows what happens. As that number n, the number of times you compound, gets bigger and bigger, heading towards infinity, the final amount doesn't just fly off the charts. It actually zeroes in on a very specific single number. And guess what? That number is E. And there it is, roughly 2.71828. And the wild part? Just like its famous cousin pi, E is what we call an irrational number. That means these decimals just keep on going, forever, with no repeating pattern. It's nuts. But for most of what we'll be doing, just thinking of it as about 2.72 will work just fine. Okay, this is where E really gets to shine, as the base of the natural exponential function, e to the x. Since E is bigger than 1, this thing is the poster child for pure, continuous growth. And all its graphs have a few things in common. See that point 0, 1? They always go through there. And on the left side, the graph gets super close to the x-axis, but never actually touches it. We call that line a horizontal asymptote. Okay, so enough with the theory, right? The best way to actually understand this stuff is to get our hands dirty. So let's run through a couple of examples to see how E works in the wild. Okay, example 1, simplifying. The main thing to remember here is that E behaves just like any other base, like x or the number 2. So all our normal exponent rules totally apply. First, let's look at the top. We multiply the numbers, 5 times 2 is 10. Then we add the exponents. 3 plus 4 is 7. Boom. The top is 10e to the 7th. Now we divide by e squared, and when we divide with the same base, what do? We subtract the exponents. 7 minus 2 is 5. And there's our final answer. 10e to the 5th. See? Not so bad. All right, next up, let's figure out what e to the negative 2 is. For this one, you're going to want to grab your calculator and find that sweet little e to the x button. Pop in negative 2, and you get about 0.1353. Now, what does that actually mean? Well, remember the graph? That negative exponent tells us we're on the left side of the chart, where the curve is getting really close to 0. So this point, negative 2, comma, 0.1353, is way down there, just hanging out near that asymptote. Now for some graphing fun. We're not starting from scratch here. We're just taking our basic e to the x graph and moving it around. So first, look inside the exponent. That x minus 2 is our horizontal shift. And remember the rule, it's kind of tricky. It's always the opposite of the sign. So minus 2 actually means we shift to the right 2 units. Then that plus 1 tacked on the end, that's our vertical shift. Nice and easy. That just moves the whole thing up 1 unit. And these shifts take our key features along for the ride. The asymptote moves up from y equals 0 to y equals 1. And our main point, 0, 1, gets shifted right 2 and up 1. So its new address is 2, 2. Okay, before we get to the really cool real-world stuff, let's hit pause for a second. I want to talk about 2 super common mistakes people make with E. They're really easy to fall into, but trust me, they're even easier to avoid once you see them. This one right here is the big one. The number 1 mistake. You see the letter E, and your brain immediately wants to treat it like X or Y, a variable you have to solve for. But you gotta fight that urge. E is not a variable. It's a constant. It's a specific number, just like pi. You'd never try to solve for pi, right? Same deal with E. It's always about 2.718, end of story. And here's a quick but super important pro tip. When you're doing calculations, always use the e to the x button on your calculator. I know it's tempting to just type in 2.718, but that little bit of rounding can actually cause some pretty big errors in your final answer, especially in longer problems. So do yourself a favor, use the button. Okay, so we've defined E, we've played with it, we've graphed it, but I'm sure you're asking why? Why does this one number matter so much? Well, now we get to the payoff. Let's see what makes E so powerful out in the real world. Let's talk about something we all understand, money. You know how a bank gives you interest on your savings, right? They might compound it once a year or maybe every month. The more often they do it, the more you earn. So that begs a pretty awesome question. What's the limit? What if they compounded it every single second? Or every millisecond? What's the absolute most your money could possibly grow in a perfectly smooth, continuous way? Well, this formula is the answer. For that perfect continuous growth, we have A equals P times E to the RT. And look who's the star of the show right there in the middle, our old friend E. It is literally the natural base for any kind of maximum continuous growth, whether it's money in the bank, the growth of a population, or even the decay of radioactive atoms. So I'm going to leave you with one last thought, and this is a little sneak peek into why E gets even more important later on in calculus. In calculus, you study something called a derivative, which is just a fancy way of saying a function's rate of growth at any single instant. And here's the mind-blowing thing about e to the x. Its rate of growth at any point is exactly the same as its value at that point. Think about that. Its growth equals itself. It's its own derivative. That perfect, unique property makes it one of the absolute most important functions in all of math. Pretty cool for just a number, huh?